Standardization versus normalization. What exactly are these techniques and why do they exist? I believe this is something all of us first need to introspect on if we were to build a good understanding of the concept. Well, to do this, let me just take an example of one sample dataset. In the graph visible on the left side, you can see that there are 13 data points and 9 of them converge towards close proximity, whereas 4 of them lie far away, right? A basic deduction all of us can make is the values that are lying far away have huge magnitude and they can have a large amount of say in the learning process, producing miscued results. Now, if I directly go ahead and perform the training without nudging the data, what do you think would happen? Well, the chances are we will have very less prediction accuracy, right? Especially in distance-based learning algorithms like the KNN, which relies on calculating the Euclidean distance between data points. That is why even in mathematics, ideas like scaling exist. In this video, we are going to break down two critical scaling techniques known as standardization and normalization. But before we do that, ensure subscribing to the Intellipaat YouTube channel to never miss any update coming from our team's end. At the beginning of this video, we just mentioned one use case of scaling when there are outliers in the data. Now imagine this. You've got a data set with 3 features: age, salary, and number of children. Simple enough, right? Now, age and number of children usually fall within pretty small ranges. Age might be anywhere from 0 to 80, and number of children is likely between 0 and 5. But salary? Oh man, salary can go all over the place. It could range from 0 to millions or even billions. Here's the catch. Because salary has such a huge range compared to age and number of children, it can totally dominate the prediction calculations. And when that happens, your model accuracy can take a drop. So what do we do about it? Here's where feature scaling comes in the picture. It's a way to ensure that no single feature can overshadow the others. Let's break it down, starting with normalization, which is also known as min-max scaling. This method transforms your data to fit within a range of 0 to 1. Imagine lining up all your data points. The smallest one will be at 0, the largest one at 1, and everything else will fall somewhere in between. So let's see how it works. You take a data point, let's call it x, subtract the minimum value of your dataset and then divide by the range, which is basically the difference between the maximum value and the minimum value. And voila, you've got your normalized value. This is super handy when your dataset doesn't have any outliers. It makes everything nice and neat, ready for your machine learning models to work on. So the next technique we're diving into is standardization, or you may also hear it as Z-score normalization. This technique is highly useful when you're working with datasets that have a normal or Gaussian distribution. So what does standardization do? Well, it rescales our data around a mean of 0 and a standard deviation of 1. It's like giving your data a fresh start, centering it around 0. Pretty neat, right? Now let's get into the nitty-gritty of how you actually standardize your data. Don't worry, it's simpler than it sounds. Here's the formula you'll be using. First, you'll need to calculate the mean and the standard deviation for your variable. Once you have those, for each value in your dataset, you subtract the mean and then divide by the standard deviation. And voila, you've got your standardized value. See, not so bad. By leveling up the competition in your data, this strategy makes it much easier to compare and analyze. Before proceeding with the hands-on, let us have a quick summary about the differences between standardization and normalization. First up, let's talk about standardization. This method rescales your data so that it has a mean of 0 and a standard deviation of 1. On the other hand, normalization is all about squeezing your data into a range between 0 and 1. Think of it like stretching a rubber band until it fits perfectly between 2 points. Now, when should you use each one? Standardization is preferred when your dataset has outliers. Normalization, however, can be your best friend when the scale of your data varies significantly, just like in our previous example of ages, salaries, and the number of children, all on different scales. Normalization helps bring everything into a neat, comparable range. And here's the best part. All this can be done in just 2 lines of code with the help of the Sci-Kit Learn libraries handy transformers, standard scaler for standardization and min-max scaler for normalization. These tools save you a ton of time and effort. Now let's go ahead and perform a quick hands-on. So as you can see, this is my Jupyter notebook. I have already written down the code for you guys and we'll go through it line by line. I've imported the libraries in the first cell, as you can see, mainly the pandas, scikit-learn and the stats model. I'm using housing dataset which I've loaded in the df variable. I have performed the basic exploratory data analysis, which is not very important for this video, so I will not go into detail. To understand the importance of normalization, we first need to observe that one of our features, which is area, varies significantly in magnitude and will definitely dominate the learnings of our dataset. So I'll just go ahead and perform the linear regression, and stats model provides us with a great feature called summary, which will help us understand our model better. So as you can see here, we have a good R-square value, which is basically a statistical measure of how well the regression line approximates the actual data. But that is not what we are interested in. We are interested in the p-value. To understand why, we will first look at the coefficients. The coefficients describe the relationship or the correlation between each independent variable and the dependent variable. The p-values for these coefficients in return indicate whether these relationships are statistically significant or not. Ideally, our p-value should be lower than 0.05 to show significance for the coefficients. But as you can see, the p-value is greater than 0.05 for the bedrooms feature, indicating a poor relationship of bedrooms with feature price. But is that the case? Let's check it out by performing normalization on the dataset before performing linear regression. So here I have initialized the scaler and trained the data using fit transform. The fit transform method will determine the parameters and basically transform the dataset. Now if I perform linear regression and look at the summary the similar way, we can see that R-square is pretty much the same, but the p-value for bedrooms has dropped to 0, which is what we wanted ideally. So I hope normalization is clear with this demonstration. Now I'll move on to standardization. I have generated a dataset having normal distribution. Again, I won't go into detail about the code. As you can see, the dataset contains outliers as well. Hence, standardization will be the ideal approach. This is how we initialize the scalar object and then fit and transform the data. As a result, you can see this is what the standardized array will look like. I hope this video was helpful to all of you guys out there. If you have liked it, hit the thumbs up button and also enable both subscribe button and bell icon to receive more updates like this. Thank you and see you in the next video.